you still writing this AO, or can I get rid of it? Are you finished with it, AO?
Yeah, finished with it. Yeah.
Okay, are we all back? If you can, because you haven't got your cameras on, I don't know if you're back or not. If you can just give me a thumbs up or unmute or something, just so I know you're back.
Oh, we're back, right? Yeah.
Okay. If you want. Amjad, are you back? Okay, well, we'll kick off again then. Now, we're going to start getting into how we design temporary works. I'm just going to show you a little method that I always find quite useful to in terms of preparing to do a temporary works design. When I joined Lang's in 1990 in the design office, this was the Lang way of doing it, and I've sort of tried to follow that on through my career. Now, what we're going to make or consider is, first of all, we need to identify the loads that act on a structure or individual members. So we need to identify the loads. Secondly, we need to identify potential modes of failure. We're then going to do a risk assessment and identify any residual risks that we can't design out. And then the last one, dare I suggest, this is the one that permanent works designers are not as good as they could be at doing. The last one, the practicality, the buildability. So if you get yourself a piece of paper, just make 4 columns. So loads, modes of failure, risks, and practicality or buildability, whatever you prefer to call it. Okay. We're going to do an example, and then I'll get you guys to do one yourselves. So the example we're going to do is a hoarding or signboard. Now, first of all, sorry, I think that's the bin then. That's the. If you can hear a noise, that's the rubbish collection. Just it's recycling on Mondays where I live. We've got to look at self-weight of these items. We've got to design for the self-weight. Wind loading and crowd loading. Okay? I'm sure you're all familiar with crowd loading. It represents people leaning on it and falling against it. And would you all agree that crowd loading is not, it can vary, it's not the same number. It depends on where your item is. Impact, could something hit it? Well, it's a possibility. Look at the photograph. What could hit that signage or hoarding? What could hit it?
Car or lorry.
Yeah, a passing vehicle. What about activities happening on site? So maybe if you've got items being lifted with cranes or excavators, we could have an impact loading. Now, what sort of modes of failure have we got? Well, overturning and sliding are fairly obvious. Overall failure. So could the whole, rather than individual parts of it, could the whole system fail? Bending. If I've got a member working in bending, if I put sufficient bending on it, it could fail in bending. Racking. So the thing falling over that way. How do we stop things from racking?
Side propping.
Either we put propping in or
Ledge.
we put bracing in.
Bracing, yes.
We brace the structure. So any bracing in this? Well, you can see some diagonals in it. Okay. Buckling. If we've got a member working in compression, it could buckle. So look at that signboard, look at that piece of advertising. What item which part of it is working in compression? What's working in compression? Well, if the wind is blowing from where the traffic lights are, can you see that raking member there? The wind is blowing from this direction. That member there now goes into compression.
Compression, that's good.
It buckle. The wind's blowing the other way, it goes into tension. Yeah? Connection failure. So we've got to join bits and pieces together here. So timber has to be joined, the metal has to be joined. So could we have individual connection failure? Now, whilst you're thinking about that, practicality, buildability. If we've got a steel structure, how can we join steel items together? How can you join steel together?
Bolt or weld?
Bolts or welds?
Bolt or weld
Well,
connection.
yeah, you could either weld the structure or you could bolt the thing together. What would you prefer to do for this circumstance? What would you rather do? Bolts or welds?
Bolt.
I think I would bolt it. Why?
Transportation.
Well,
Easy to install.
I think you've got a couple of issues here. First of all, you could build it in situ. So you could build it standing up like this. But by doing that, I'm creating a work at height risk for operatives, because somebody's going to physically get up there and put it together. So if we wanted to get rid of that risk, how else could we build it?
Was before erecting it, behind the shop.
So we could build it on the ground, yeah, and then maybe we could lift it into position with a crane. Okay? So if we got to lift it with a crane, we then need to think about lifting points. And when we finish with this 2 years later, is it easier to take bolts apart or start cutting welds? I think I'd rather take the bolts out. So we've decided we're going to bolt this whole thing together. There's going to be quite a lot of bolt holes. What's the chances of every single bolt hole being exactly in the correct place? Come on, fellas, you know as well as I do that. That just doesn't happen. It never happens. It never happens. Yeah. On site, Derek, we have this wonderful thing that we cling to like drowning men. It's called construction tolerance. So how do you, as a designer, introduce a bit of... Because believe it or not, as a contractor, I cannot build things exactly, to the nearest 1,000th of a millimetre. Okay? I just can't do it. So how do you as designers introduce a bit of tolerance if we've got a structure which we want to bolt together?
Slotted holes.
You'll know. Maybe you have to start slotting the holes. There you go. You've introduced a little bit of tolerance for me as a contractor. Okay? Now, one last mode of failure maybe to think about. A lot of these hoardings and signboards, what we tend to do is dig a hole, put a bit of concrete in, and then concrete it into the ground. If we don't make the hole big enough, deep enough, or wide enough, could the foundation underneath it fail? Quite possibly. All right, so you get the idea. So hopefully you've got a piece of paper in front of you with these 4 columns on it. We're going to start looking at shuttering. So what I want you to do is do that exercise, this exercise, for this example. The piece of shuttering, it's when they were building Terminal 5 at Heathrow. And what they're building is the baggage handling tunnels. Okay, so when you go to the airport and you check your suitcases in, and you're going to Italy and your suitcases are going to Spain. Ash, this is where they lose them. Okay? In all these tunnels, this is where they lose your suitcases. So you get off the plane at the other end, where the hell have all my suitcases gone? Just to give you an idea of scale, we're looking at a shutter about 7 metres high, so we're going to pour about 6 metres of concrete. Okay? And this shutter has to be reused many, many times. Okay? They've got to build, I think, about 2 miles of baggage handling tunnels. So they're going to build this shutter, fill it with concrete. Concrete goes hard, strike the shutter, move it on. Fill it with concrete, wait for the concrete to go hard, strike it, move it on. Okay? So just spend 5 minutes filling some of this in.
Sorry, Ray, what's the last step of design? I've got
Let me
loads.
just go back to this. So you could call it practicality or buildability, whichever one you prefer.
But no.
So that's your CDM obligation. Think about how the buildability of it. That could be how you move it, how you're going to make it. What do you think is important? I encourage you all to have a good think about this last one, the buildability, the practicality. So what sort of practical considerations might you need to consider if you're responsible for designing shows?
Structures.
All right, should we have a little go through this? Hopefully you've all had a few minutes to think about it. And I would encourage you to do this and use this as a bit of a checklist almost. Okay, so you say, well, I've calculated that load, I've calculated that load, I've calculated that load. Yep, I've checked that mode of failure, I've checked that mode of failure, I've checked that one. And just sort of tick it off. So these are some of the things I would hope you would be thinking about. For me, the loads would include things like the pressure of the wet concrete inside a shutter.
Yep.
For concrete, because we may have a case where the concrete is allowed to drop down the shutter. Wind. Would you all agree a piece of shuttering like this is a fairly big sail?
It is.
Yeah?
It is.
I mean, that's a pretty substantial sail, isn't it? So you imagine a big storm gets hold of that. Other environmental loads. For example, snow. Is there a possibility we could have a build-up of snow on that shutter? We're doing a job in winter. Yeah?
Nice.
If you're working in Kuwait, I'm guessing that's not going to be a major problem. Yeah. Accidental impact. Is there a possibility a vehicle or a crane could hit this? Now, people always ask me, well, hoardings, scaffolds, shutters, how the hell do I design it for an impact from a lorry driving into it? The simple answer is you can't. If a lorry drives into that at any speed, it falls over. So if you can't design it to withstand a lorry impact, what do you then have to do? What's the practical solution to that if you can't design it for being hit by a lorry?
manage risk on site, manage the
You have to stop the lorry driving into it in the first place. So how do you do that?
Put a barrier in front of
Yeah,
the.
maybe you put some of those concrete barriers up. You have some sort of exclusion zone for vehicles. So if you can't physically design it to withstand a lorry drive, can you imagine what sort of scaffolding you'd need to stop a lorry driving into it?
You,
I mean, it just absolutely, yeah, absolutely. So the idea then is, Derek, if you can't, if it's going to collapse because the lorry drives into it, you have to stop the lorry driving into it in the first place. Put some big concrete barriers up, set up an exclusion zone, whatever you need to do. Self-weight, we've got to consider self-weight, live loading. Now, would you agree at some point people have to get up here to physically pull the concrete? Live loading.
yes, they have. Yeah, live on
Vibration. When we poke at a concrete to get the air out, we could have vibration. Now, fatigue. In temporary work, fatigue is not something that we get worried about very often. Things like shutters, the components simply don't get used often enough. The way we manage fatigue is through inspection. If we see a component is looking a bit knackered, we just don't use it.
like the lifting well.
Sorry, say that again?
I feel like the lifting well because you lifted it many times. You said it was 2 miles of
Yeah,
concrete.
but we're looking at, okay, 2 miles, you might use it 100 times. Will a piece of metal fail in fatigue after 100 uses? 100 million uses, maybe, not 100 uses. The only exception for fatigue, I would suggest, would be things like temporary bridges. Yeah? How many of you gents have seen sometimes when they do work on highways, they have to redirect the traffic over a temporary bridge whilst they build a new bridge? Well, again, you could have, thousands of vehicles driving over that bridge every single day. Fatigue starts becoming a problem. On scaffolds, shutters, it's not a problem. Okay? Sometimes if we have to put something into flowing water, you might have an effect from flowing water. Thermal. Again, it's really something we don't worry about in temporary works. Expansion, contraction. The only exception I would suggest is very large excavations where you've got really, really big props. They can be affected by the difference in temperature between day and night, where the metal will expand and contract. On shutters, it's not a problem. Okay? In some parts of the world, you might be worried about earthquakes. Again, in the UK, it's not something we would worry about. If you're working in, Chile or Japan, you might be worried about earthquakes, not in London. And you might need to support the cage using the shutter, stability of the cage. Now, modes of failure, well, bursting. If the pressure is too high, the shutter could burst. It could overturn or slide. Bending, buckling, shear, all fairly obvious. I mean, buckling, what members are in compression? Well, that member there could be in compression. If you've got people standing here, that member there goes into compression. If the wind is blowing from this direction, that prop goes into compression. So you could have a buckling failure. Tensile failure. Well, if the wind is blowing the other way, that member now goes into tension. What stops the two faces of shuttering from moving apart when we fill them with concrete?
boards.
Ties. So we put ties through the shutter. If you've never seen them, this is what they look like. You'll have one on each side of the shutter. That bar goes through the concrete. Please, gentlemen, it's not just me who has bits of shuttering in their office.
Sorry, can you show that again?
It's just you.
Tell me it's not just me.
It's just you. It's just you.
The cranes, yeah. Cranes and shuttering and yeah. I need to get out more, really, don't I? I need a hobby. Foundation failure. If the whole thing is really, really massively heavy and the ground is really bad, it could fail. Lifting. So when we're lifting the shutter, it could fail because we design it for a pressure. We need to consider lifting. Now, deflection. If your shutter deflects too much, now the components haven't physically failed. We haven't lost any concrete. All that's happened is the shutter is bowed. Could that also be deemed a failure? Why? Why could that be deemed a failure?
Introducing air pockets.
Not necessarily. You pokered the concrete properly, so we've got all the air out of it.
Aesthetic failure for the client.
Yes. Is there a possibility your client comes along, Phil, and says to you, look, I'm paying you to produce concrete that looks like that. You're producing something that looks like a very heavily pregnant woman. I don't like how that appears. I'm not going to pay you for it. Would your client be within their rights to do that?
Yes.
Absolutely. If you don't meet the client's expectations, they're not going to pay you for it. Yeah? If you go to a restaurant and ask for a steak supper and they bring you a cheese sandwich, you say, well, hang on a minute. What's going on here? Connection failure. Now, risks, obviously things like work at height and access, falling objects. Does anyone know what Lola is? What's Lola?
Lifting regulation.
Yes.
Ray, just a quick one. Modes of failure, you missed one. I don't know if this comes under it. When the shutter lifts up due to hydraulic pressure.
Right. I will come back to uplift later on.
Okay.
You're in about 2 or 3 hours' time, Derek. For something like this, I would not be concerned about uplift.
Okay, cool.
I will explain why. Give me a couple of hours, mate. Okay, and you'll know.
That's fine. Yeah,
Right.
that's fine.
Lola, lifting operations, lifting equipment regulations. Okay, so if you've got to lift heavy objects, there are regulations that cover how we do it. Now, Peter, in the Republic of Ireland, you've got your equivalent of our Lola regulations. Others, things like we need lift plans and certification for all the lifting kit. Incorrect or fake components. So people simply putting the wrong components onto a shutter and it fails. Or in our industry, we have had issues with people buying cheap, fake components. Okay? Made to very, very poor quality standards, made from very poor quality material, and it simply fails. Now, let's look at practicality. Okay. So, these are the sort of questions I would be asking. Do we want to manufacture this shutter on site or manufacture it off site and get it delivered to site on the back of a lorry? If you want to make this off site, okay, and then transport it, we need to consider transportation. Yeah? Why design something, 7 meters high, 12 meters wide? Because what's going to be the problem with that?
Highways Authority will give
How
you
the hell do you get it on a lorry to transport it to your site? Yeah? Some countries have things called bridges. How the hell are you going to get it under a bridge? So, as designers, you need to think, well, maybe we need to make this in smaller sections, simply so we can put it on the back of a lorry and transport it to site. Yeah? There's no point in designing the whole thing in one go, because you can't transport it anywhere. What about things like, are we going to use proprietary equipment, or are we going to manufacture it from our own components, so things like timber, or are we going to use proprietary aluminium equipment? How are we going to put it together? Now, lifting. Okay, let's pretend this is a shutter. If I want a shutter to hang exactly vertical off a crane, exactly vertical, how do I make sure that this hangs vertical? What have I got to do to make is vertical.
Any sense of
PG.
The centre of gravity has to be directly underneath your lifting point. Okay?
Yeah.
The centre of gravity is about there. I'm holding it there. It's probably in line. What would happen if I held it there? If I let go with this hand now, what happens to it?
centricity?
It swings until the centre of gravity lines up with one. Tell me, gents, do I want to lift the shutter so it's exactly hanging vertical? Yes or no? You got a 50-50 here, gents. Yes or no? Give me a thumbs up or a thumbs down.
Yes.
I would say no. Okay? I do not want the shutter hanging exactly vertical.
Becomes a sale.
Then if this is where your shutter needs to end up, this is where your reinforcement is and everything else, you can either have the shutter lifted in like that, leaning like that, or leaning like that. Okay? So thumbs up for A, thumbs down for B. A or B?
I'd say A. Go for A.
Derek, unlucky. Don't buy any lottery tickets on the way home tonight.
I don't gamble.
You're going to lose every time, I'm afraid, my friend.
I don't gamble at all.
Don't bet on the horses. Right. If we go back to the photograph here, does anyone know what we call this little strip of
Kicker.
called a kicker? So when we build a slab, we normally build a little upstand, which we call a kicker. There's the kicker. Okay? I would design my shutter so it hangs slightly away like this. Okay? Look what happens. I bring the shutter in, we line it up with the bottom of the kicker. You then jib up with the crane, so you pull with the crane, and the crane pulls the shutter into the vertical plane. Okay? And we want to take it apart. So what we do is we got these ties. So we remove these. Okay? So we put a crane hook on it. We remove the ties. And what does the shutter want to do when I take the ties off it? It wants to peel away from the concrete. Okay? In my opinion, the one thing you don't want to do is that. Because think about it. You bring the shutter in. The first thing it does, it hits all the reinforcement. So is there a possibility it could push the reinforcement cage over? Well, it could do. And secondly, I promise, gentlemen, there'll be an awful lot of swearing going on site when the boys on site are trying to push the bottom of the shutter up against the kicker. And when you take the ties out, the shutter doesn't naturally want to fall away from the concrete. So, as designers, gents, just by moving your lifting point very, very slightly in relation to the centre of gravity of what you're lifting, have you made the job easier or more difficult for the people on site? What do the CDM regulations require you to do?
The risk.
Got to make it easier. You've got to minimise, reduce the risk. By getting the lifting point wrong in relation to your centre of gravity, I think you have increased the risk for the people. Be honest with me, have any of you ever thought about something like that as designers? Do you think that's something you should be doing under CDM regulations? 100% you should be. 100%. You then need to consider things like productivity. People want to, pour the concrete, strike the shutters, move them on fairly quickly. How will we get all of this inspected? How do we vibrate it and place the concrete? Surface finish. Okay. What has the biggest effect on the appearance of your concrete? The material you use to form the surface of your shutter.
Yep.
more often than not, plywood. Okay? So here's some fairly standard shuttering plywood. So your choice of plywood, and this is just 4 examples, your choice of plywood has a big difference to the appearance of your concrete. Okay? So would it make a difference if the concrete you wanted was for a foundation, or if it was going to be exposed concrete that people could see? Would the finish make a difference to you?
Make the difference if it's going to be exposed for people to see.
Yeah, absolutely. Would you agree, for a foundation, how many of you gents really would be worried about the foundation, the appearance of the foundation?
No.
Come on, fellas. If any of you lot ever turn up on site and you say, I don't like the appearance of that foundation, I hope the site team dig a hole and bury you in it. Yeah? I really hope they do. Okay? Come on, if you're going to bury it, as long as structurally it behaves like you want it to behave, so they've got the right dimensions, they've got the right cover on the rebar, there's no blow, they vibrated the concrete properly. Its appearance is a little bit rough. So what? But if it's exposed concrete, so the choice of material now makes makes a massive difference. So are we happy that we understand how this little system works? Okay. Now what we're going to focus on now is the first thing here: concrete pressure. Actually, before we do, whilst I've got this presentation up, right? Whilst I've got this presentation up, hang on a minute. Let me just share this again with you. Get yourself a pencil and paper. Now, for temporary works, I think there are 6 dominant load cases that we're going to consider. Let's see how many of you vaguely remember some of this. By sharing this, can you see a simply supported beam?
Yes, I can see this.
And I've applied a uniformly distributed load to it. And I'm going to call the load W, little w per metre run. Now, I know some engineers use big W, which is the total load. I use little w, which is the load per metre run. Can anyone tell me how I work out the reactions? What's RA and RB?
WL by WL/2.
Do you know what? If you guys don't know that, we're in trouble. Yeah. You
I
also
had to answer the question because I didn't know what you are driving at. Obviously, it's too.
it was too simple. So what we're saying is half the load goes down A, half the load goes down B. Now, when I apply the load, it bends like that. Where is the position of maximum bending? Middle. Who can remember the formula for working out the bending moment in the middle? Maximum bending moment.
L squared over 8.
WL squared upon 8. Okay? And this is the one some people might not remember the top of their head. I mean, shear, I'll tell you now, gentlemen, for the vast majority of temporary works, shear is not a major problem. Connections, but for things like shutters, shear is not a major problem. It is. So we have an approximation, a little formula for working out the deflection. Who can remember that formula? 5 over 384 WL to the 4th over E. Now, what's E?
Young's modulus.
Young's modulus. What is Young's modulus?
Stress or strain, yeah.
It's a relationship between stress and strain for a material. The property of the material. What's I?
Moment of inertia.
Or second moment of area, moment of inertia. If I had something which was something like that. What's the second moment? What's the moment of inertia? Second moment of area for something like that, where it's D and B.
E cubed over 12.
Very good. Okay. That's good. Some of you went to university and learned something, didn't you?
Not at me.
Yeah. Some of you, I think, just went and had a good time. Yeah. Probably at the expense of the taxpayers. Now, when we multiply E and I together, we call it stiffness. Now, I can change stiffness one of two ways. By either changing the material, so instead of having a steel beam, I could change it to a concrete beam or a timber beam. Therefore, the E changes. Okay. Off the top of your head, anyone know what the E of steel is? What's the Young's modulus for steel? About 205 times 10 to the 6 or something like that, isn't it? Yeah. What's the E for timber or aluminium or concrete? If you don't know, what do you do? That's what Google was invented for. That's why somebody went to the trouble of inventing Google. Just Google it, fellas. The only one I bother to remember is steel. I mean, concrete's about 1/10 of steel, but I've got no idea what the Young's modulus for aluminium is. I'd have to look it up. Okay. Now, so if you change the material, you can change the stiffness. You can also change stiffness by changing the shape. So instead of having a rectangle, I could change it to a circle or a triangle or a square, and I would change the I, therefore I change the stiffness. Okay? But when we multiply E and I together, we call it stiffness. So hopefully you all remember that. Now, there's a couple of little tricks we do in temporary walls. Trick number one to look out for is we can consider continuous beams. A lot of the items of temporary works we design, we can consider what we call continuity. Now the rule is, in order to consider continuity, you need a minimum of 3 spans and 4 supports. Now, if you've got more, not a problem. If you've got less, you can't start taking full continuity effects. And what happens is it deflects a bit more like that. And what happens is the supports in the middle attract a little bit more load than perhaps you think they do. We have these things called continuity factors. Can you remember how much more load does support B and support C attract compared to what you think it might? What's the continuity factor for this case?
1.25.
Nope. Nope, not for this. It's 1.1.
I know it's less than that.
Yeah.
It's
So what we have, if you've got a minimum of 3 spans and 4 supports, the 2 central supports take an extra 10%. Now, to maintain static equilibrium, whatever load I've got coming down has to be equal and opposite to the reactions. So my reactions have to add up to the total load. The total load is 3L multiplied by W per meter run. So all of my reactions have to add up to that. If they don't, I've got a mechanism. So therefore, RA and RB is WL times 0.4. So when you work it out, 2 of these plus 2 of these gives us 3WL. So what happens is the central supports take a little bit more load, but reduces the bending moments. What's the worst case bending moment for this scenario? What's the formula for the worst case bending moment? Who can remember this? Oh, come on, fellas. Don't let me down. W squared upon 2. Okay? And because the bending moment reduces, the deflection will reduce, and the approximation we use is 3/3. Now, there is one special case which we need to just be mindful of. And this is your chance to shine. RB, what's the continuity factor that we use for RB?
1.25.
Thank you. 1.25.
I know you're trying.
So to maintain equilibrium, the end reactions are 0.375. And for this load case, I simply consider bending and deflection as being simply simple. So here's a little trick for you, gentlemen. If you want to designers, you have to start smoking. you have to. Part of this course is I've got to teach you how to smoke again. Now, here's a very, very easy trick. If you want to check something in bending, what is the worst possible bending moment we can have in bending? WL squared upon 8. If you check something for the worst load in the biggest span and do it for WL squared upon 8, and you can prove it works, it works. Okay? You don't need to do any other checks. You've checked the worst possible condition. What is the worst possible reaction we can have? This one here, 1.25. So you take your biggest L, your biggest W, multiply it by 1.25. If you can prove it works, it works. You don't need to do any other checks. You've checked the worst possible condition. Okay? I have had designs submitted to me, and my favourite one was for a force work scheme. And the engineer had modelled every single span, every single concrete load. Okay, there were over 400 pages of computer analysis, and they wanted me to produce some check calculations. I found the biggest span, the biggest load, did WL squared upon 8, WL times 1.25. It was half a page of calculations. Okay. Now I'll tell you how long ago this was. Okay. I had to fax. Who remembers fax machines? Who's old enough to remember fax machines? Yeah, those stupid noises those bloody things made. Yeah, sounded like aliens landing. I faxed my check calculations, half a page, to the site. I remember the site manager phoned me up. He said, "Oh, I think our fax machine has run out of paper or is broken. We've only got one page of check calculations. Where's the rest of it? So we don't need any more. You've got all the check calculations you need. Yeah? I've checked it for WL squared upon 8, WL times 1.25. I proved it works. You don't need any more check calculations." And yet the designer had produced 400 and something pages of computer analysis. What a complete, proverbial. What a wally. Now, we don't always consider UDLs. Sometimes we might have a point load. So hopefully you remember this. So your reactions are just, there's not PL over 2, should be P over 2. Sorry, typing over there. Your bending moment is PL over 4, and your deflection is 1 over 48 PL cubed over EI. So I need to change that to P over 2. And occasionally you might have cantilevers. So if you've got a cantilever with a UDL on it, using a formula. And the last one is if we have a point load on the end of the cantilever. What I recommend you, if you haven't got time to write this down, get your camera, get your phone, take a photograph of the screen. Okay? If you can't remember all of these, okay? Just take or screenshot. Just take a picture of what's on the screen.
The screenshot actually, yeah, screenshot better.
Whatever's easier for you. What you'll find, if you can remember those 6 conditions, you know what, you can design almost all temporary works. Okay. All right, so let's start doing a little bit of proper design. Can you all get your folders, or those of you who've got the notes electronically, can you find, there's a section that on the bottom, my numbering system, it'll be RKF, and then there'll be a number and a revision. So the section you want is RKF 200K. Right? The first page says concrete and concrete pressures. Those of you who've got the folder, just look through it. Look at the numbers at the bottom until you see RKF 200K. Just give me a thumbs up if you found it, please. First page says concrete and concrete pressures. Whereabouts in the folder is it, AO, roughly? Is it sort of in the middle, at the beginning?
Yes. I think the 3/4 half done.
Okay, about 3/4 of the way in. Okay.
Yes. And concrete pressures.
Have you all managed to find it?
Not yet. Still searching.
Moment. The first page. So look at the bottom of each sheet. You've got a system. It says RKF, and then there'll be a number. You go into an RKF 200. 200. Has anyone not found it, by the way?
210G.
Just before that, go back. So it'd be before that.
Was it 200K, is it?
Yeah.
RKF 200K.
200K. That's the one.
Page 87.
The first
Page 87
Yeah,
of
the
112.
Okay.
If anyone.
The first page will say concrete and concrete pressures.
Found it.
Now the main
Cool.
Yeah, you got it right. Good. So the main load that we design shutters for is concrete pressure. Now, this is the main reference document for this subject. Formwork, a guide to good practice. I'm one of the people responsible for writing this. And if you're serious about designing and getting involved in shuttering, then I recommend you get a copy of it. Okay? Get a hard copy or download it. Okay. This is where things have changed during my working life. When I started on site 30-something years ago, I was very quickly sent on some training courses, and it was expected that a young site engineer like me, we would design our own small shutters on site. We would then buy some timber, some plywood. We either had our own, these metal components, or we hired them, and we would design and make our own shutters. That happens a lot less now than it did 30 years ago. For one simple reason, a lot of sites hire shutters. Okay? And the argument is, why invent a wheel if you can simply go and hire a wheel? Okay? And there's lots of companies that specialise in the hire of shuttering. Has anyone heard of this company, a German company called Perry? They're one of the biggest suppliers of formwork systems in the world. Okay? And you can hire some of their shutters. Now, they will tell you, so on the information they provide, they will tell you the maximum pressure that their shutters are designed for. So, for example, they might call it a P60 system, P60. What that means, it's designed for a maximum pressure of 60 kilonewtons a square metre. A couple of questions for you. Number one, permissible stress or limit state.
Permissible stress.
Correct. Permissible stress. So what does that mean?
It's stress you can put on the shipper before you have to call the ambulance.
Now, or your insurance company.
Oh, your insurance company.
Safe working load. Okay? So if they say the shutter's been designed for maximum pressure of 60, you could put a maximum pressure of 60 on. Okay? Now think about that number for a minute. What's that in tons? What's kilograms in tons?
6 tons.
6 tons. And do you remember those 4 pictures I showed you this morning? What was our picture that represented a ton? Car. So just think about what I'm saying here, gentlemen. If you took a meter by and that's every meter. Who's surprised about how strong this stuff actually is? I don't know about you guys, I think that's pretty impressive. You get a meter by meter string, you can put 6 cars on it. I think that's impressive. Now, they will very clearly say, we will get you, and our shutter takes that pressure, providing you build it correctly, use it correctly, and it's the user's responsibility to make sure that pressure exists. So we need to understand how we work out the pressure. Because if we're using a hired system to make sure we don't exceed it, if we're designing our own shutters, we design it for the maximum pressure that we calculate. Okay, this is how we do it. Now, pressure is the height times the weight. Weight is density times gravity. Now, if we consider water, water is 10 kilonewtons a cube. So if you've got a meter of water, the pressure a meter down is 1 meter times 10. Meters of water, 2 times 10. 5 meters of water, times 10. Nothing complex. Tell me, what's the weight of concrete?
25 kilonewtons.
Yeah, it's about 25 kilonewtons a cubic meter. About. So what we say concrete is about 2.5 times heavier than water. So when concrete is wet, the pressure increases 2.5 times faster than pressure. But there is a subtle difference. Don't even think about this. Give me the obvious answer.
Rise up.
It goes up. It sets. It goes up. Fellas, isn't it? Yeah? There's a clue there. If you ever visit a site, gentlemen, and we build a shutter, good practice on site is they should fill shutters in layers. So we fill shutters with concrete in layers. If it's a big piece of shuttering, it could take the people on site a long time to fill that shutter with concrete. Trust me on this, it is not unusual. The first lorry of concrete turns up on site at 8 o'clock in the morning, and they put it in the bottom of the shutter. It could be 4 o'clock in the afternoon, they're pouring the last bit of concrete at the top of the shutter. Do you think the concrete at the bottom has already started to harden a bit by the time you put the stuff at the top?
Yep.
Yeah? If you don't believe me, get yourself a wheelbarrow, mix some concrete first thing in the morning, okay? Leave it for 8 hours, and then see if you can get the concrete out of your wheelbarrow. Okay? You're going to need a pickaxe, and afterwards you need a new wheelbarrow. Okay? So the subtle difference is, gentlemen, water pressure simply keeps increasing, whereas there comes a point with concrete pressure where it tails off. Because the theory is, we leave concrete alone, it will harden, it will set. That's the theory. That's it. Now, there's 2 ways of doing the calculations. First one uses a formula. So if you've all got that section, turn to page, I think it's 4 of 10. And about halfway down the page, you'll see a formula, which is this one here. Okay? And it's got C's and square roots and K's and H's and things in it. And it's not that user-friendly. So what people have done is they've taken that formula and they put it into a table to make it a bit easier. So have a look at the next page, page 5, and I'm hoping you're all looking at this table. And just give me a thumbs up or say yes that you've all got this table in front of you.
Yeah.
You'll manage to find it. Okay, good. Who's seen this table before? Anyone seen this before? Okay, well, not to worry. Don't panic. I'm going to show you how to use this table. But then I'm going to throw a spanner in the works and tell you this table is now redundant. I'll show you the new versions. And I promised if you can drive this, you can drive the new ones. And the way we're going to do, or what we're going to do is an example, and then there's a tutorial for you guys to have a go. So this is the example. So we want to build a piece of concrete on site and we need some shuttering. So just follow this on the screen if you could. So the first thing we do is calculate the volume. 50 cubic concrete. Okay? Half a metre thick, 5 metres high, 20 metres long. Okay? Now, go back to the chart. Here it says columns, here it says walls and bases. Column is when the plan dimensions, length and breadth. Forget the height, don't worry about the height, length and breadth, both less than 2 metres. Is this a column? Is this example a column?
No.
Because that is a lot more than 2 metres. Okay? If that dimension there was 1.5, it would be a column. But this one is a wall or a base. Next dividing line is across the middle. It separates different concrete mixes. The group 1 is concrete made with CEM 1. I think most people still call it OPC. What's OPC?
Ordinary Portland cement.
Very good. What's SRPC? The next one. Sulfate resistant. Yeah. Where do we tend to use sulfate cements? Well, where salt could be an issue. Or, who's old enough to remember RHPC? Who's gonna give the age away?
Is that what they used to build the pyramids, Rick?
It's something like that, yes. Very similar, Derek. I think it's what Noah used.
Rapid hardening.
Rapid hardening Portland cement. We don't use it anymore nowadays.
Okay.
But can you see here it says without admixtures? A group 2, same cements, but it says any admixture except the retarder. What does the retarding agent do?
Those on the way to curing.
Correct. So let's go back to our little diagram here. Let's assume this is a pressure diagram for an ordinary concrete, and that happens to be the maximum pressure. Doesn't matter what the number is. If I put a retarder in the mix, would you expect the maximum pressure to be slightly higher or slightly lower?
Higher.
What would you expect?
They're higher.
Higher.
Yeah.
Correct. Yeah. Why? Because the concrete down the bottom isn't setting quite as much when you're pouring the concrete at the top. The reason we've got a line across the chart is below the line we put something in the concrete to slow down the chemical reaction. So perhaps you're using a retarder, or have you come across these cement substitutes? The two most common ones would be ground granulated blast furnace slag or pulverized fuel.
Mm-hmm.
They both have the effect of slowing your concrete. But for my example, let's just use ordinary Portland cement, OPC. So that puts us into here. So can you see we're in this quadrant here? Next variable, concrete temperature. Not air temperature, temperature of the concrete when we're placing it. How do we know what the placement temperature of concrete is?
Measure it.
Somebody on site should be measuring it.
Measure it, that's all.
Yeah, it's part of the quality process we should be checking the temperature of the concrete. Now, when I was on site, what used to happen was the first lorry of concrete turned up. We had a big metal plate. We put about a third of a cube of concrete on it. You mix it up a little bit. You then did your, who remembers doing slump cone tests on concrete? The little
Slump
metals.
test.
Yeah, you did a slump test. You then probably used some of the concrete to make some cubes so you could test them. We used to have these big thermometers made of brass they used to put in the concrete to measure the temperature. Okay? And they were an absolute pain to clean afterwards. Nowadays, what I've seen is it's a big needle, you poke it into your concrete, there's a wire, a little data logger, and it tells you the temperature. Okay? A bit like one of those things to check in to see if your chicken's cooked for your dinner. You put it in the chicken and it tells you what the temperature inside the chicken is. Yeah. Now, remember, this is temperature of the concrete. Specifications, the specification will say you are allowed to pour concrete, or it's the same for mortar, for laying bricks, when the air temperature is what? What have you gents seen in specifications?
5 degrees.
It normally says something like 5 degrees and falling, or it might say 2 or 3 degrees rising. But can you see the concrete itself has to be just a little bit warmer? What happens before below to water?
Ice falls.
Starts to freeze.
Yeah.
What can happen if your concrete starts at more than 15? What can happen to the water there?
Evaporate.
Correct, it could evaporate. Why?
Mm.
Why could the water evaporate? Well, gents, what's the chemical reaction between cement and water called? What do we call a reaction?
Exothermic reaction.
No, that's the type of reaction. It's called hydration. What type of
Exothermic.
is it?
Exothermic.
Exothermic. What does that mean?
Yeah.
It generates its own heat. Yeah. Now, gentlemen, we've got to be really careful here. When we're pouring a lot of concrete, that temperature, that exothermic reaction can be a massive problem to us. Okay? What can happen is, in effect, you can cook your concrete. The water will evaporate very quickly, so you could get a loss of strength. You could, it'll probably set really fast on you, and you'll end up with a load of joints in your concrete. Or, what happens is a surface will just crack on you. You've let it dry out too fast. Are any of those three something that we want from our concrete? No. Careful with temperature. You don't want to let it freeze, and you don't want to let it cook. Now, in the UK and Ireland as well, Peter, what we normally say is 5 is winter, 10 is spring and autumn, 15 is summer. Okay? And I pretend it's summer, okay? Pretend it's August, and let's call it 15 degrees C. Okay? So it's 15 degrees C. Now, next thing we want is the height of the shutter. Would you agree, if they were going to pour 5 metre height of concrete, the shutter needs to be just a little bit more than 5 metres high?
Yeah, that'll be. It should be.
Tell me, gents, what's the point in building a 10 metre high shutter if you only want a 5 metre high wall? What's the point of why would you do that? What's the point of that? Tell me, fellas, why would you buy size 15 shoes if your feet are size 8?
Give you room for error.
Room to grow, Derek. Yeah, you grow into them. They was on sale, weren't they? Fellas, if you've got size 8 feet, you're not going to buy size 15 shoes unless you want a job in the circus as a clown. Okay? Just take it as the height of the concrete. You don't need to do this to the nearest millimetre. Just call it 5. If the shutter's 5.1 or 5.2, just call it 5 metres. Okay? Just keep it simple. And the last thing we want is rate of rise. Okay. you need to have a little bit of an idea about productivity. How quickly can they pour concrete on a site? Now, the two common ways of pouring concrete, the first method will involve a concrete pump. So they hire a concrete pump. The second method is they use a crane with just a big bucket on the end of it. Okay? If it's a foundation, you pour it straight out the back of the lorry, but not when you've got a 5 metre high shutter. Okay, productivity. If a wagon of concrete is 6 metres, on an average day, on an average site, it takes them about half an hour to do a lorry of concrete. Okay? So per hour, they do about 2 lorries of concrete. Some jobs a little bit more, some jobs a little bit less. So on average, you would say somewhere between 10 and 15 cube an hour on average. Okay? With a pump, you normally do, it's quicker. And normally you'd say about a lorry every 15 minutes. So if you said somewhere between 20 and 30 cube with a pump. Okay? Now, these numbers you'll have to get from your customer. Okay? These are the numbers you'll have to get from your customer. It should be on your design brief, I hope. Some idea of productivity. Okay? But on average, I'd expect a crane and a skip somewhere between 10 and 15 cube an hour, with a pump somewhere between 20 and 30 cube. Okay? On average. So, let's go back to our little. Let's say we're using a crane and a skip, and I'm going to take an average. I'm going to say 12.5 cube an hour. So it's halfway between that, 12.5 cube an hour. So if we have 50 cube of concrete to pour, and the site can do 12.5 an hour, it takes 4 hours to fill the shutter. Okay? Now this is the mistake a lot of people make. 4 is not your rate of rise. That's how long it takes to fill the shutter. So after 1 hour, your concrete's got to there. 2 hours, 3 hours, 4 hours. So your rate of rise is that increase per hour. And the shutter is 5 metres high. It takes them 4 hours to fill it. When I went to school, 5 divided by 4 was 1.25 metres per hour. Can you see how I've ended up with that 1.25? That's the important number. Okay. Let's do another example. Let's say we're pumping the concrete. Let's call it 25 cube an hour. How long will it take them to fill using a pump at 25 cube an hour? How long does the job take? Go on, unmute Ash, you're muted. 2 hours, yes?
Yes, 2 hours.
Yeah. So what's the rate of rise with the pump? 2.5 metres an hour?
Yeah,
Just give me a thumbs up that you understand this rate right, because this is the important bit. Okay, so let's go to our chart. It's a wall or a base because of the dimensions. We know the concrete from the specification, the delivery ticket, the design, whatever. We know the temperature. I've said it's going to be in the summer. We know roughly how high the shutter's going to be. 5 metres high. So you're halfway between the 4 and the 6. And the bit we've had to calculate is the rate of rise, which is 1.25. So you go down the middle there. You go across the middle there. This one, it happens to end up in the middle, so where the lines cross. Sometimes it lands on a number, which is easy, but this one happens to be in the middle. Again, gents, don't try and make it complicated. All I tend to do is just take the average of the 4 numbers around it. So we've got 45, 50, 50, 55. On average, it comes to 50. So for this one, I would expect the maximum pressure to be 50 kilonewtons a square metre. Now, if I was checking a design from a proprietary company or a proposal, if the site are going to hire a shutter that's designed for 60 and you've worked out a maximum pressure of 50, have we got a problem to worry about?
No, no. You have 10 kilograms that's spare.
Yeah. But just remember this, gentlemen, not all shutters are good for 60. Like not all speed limits are good for, not all speed limits are 60. You could hire a shutter that's good for 30. Yeah? It's a much cheaper, it's a much weaker system. Does your customer potentially have a problem if they've hired a shutter that's good for 30 and they want to put a pressure of 50 on it? What's likely to happen to that shutter?
Was that going to be swimming?
You got a lot of wet concrete to shovel up.
Was it going to be swimming? It's going to be pissed at you.
Absolutely. Yeah. Is that a major problem that you need to highlight to your customer?
Oh, yeah.
Absolutely. All right, so let's give you a quick update. And then we got sort of a little bit of time to do the tutorial. The chart you've seen is about 45 years old. The single biggest change in the last 45 years is concrete technology. The types of concrete mixes we use now are very different to 30, 40 years ago. So look at the next page. A few years ago, a university in Scotland was paid to do some research on modern concrete mixes. And they've reclassified modern concrete into 3 different groups, A, B, and C. On the old chart, you were either above the line or below the line. You had a choice of 2. We've now got a choice of 3. And for each of these categories, these groups, there's now a new chart. So look at the next page. You've got a chart that says Group A. Take up to that, we'll say Group B. And guess what the page after that might say? Okay. So all they've done is split the one chart into 3, depending on what concrete you're using. Okay. The rest of it is exactly the same. So column is 2 meters by 2 meters. You've still got your height and your rate of rise. What have you noticed different about these new charts? What's the most obvious difference? Temperature. Okay. Nothing to do with global warming, gents. It's not to do with global warming. There are 3 factors that come into this. Number 1, it includes the effects of working somewhere hot, in hot countries. What would you suggest is somewhere hot?
Snowy.
I thought you were going to say Birmingham. To the best of my knowledge, Birmingham doesn't have a subtropical climate. Okay? If you're working in the Middle East, if you're working in the Australian outback, if you're working in Death Valley in California, okay, it's a bit hotter than Birmingham. So be careful if you're working somewhere properly hot. Secondly, if you're pouring concrete a long way below the surface, you're doing tunnels or deep shafts. As you go down, temperature increases. So if you're doing a tunneling job. And the third one is if you're pouring incredibly high strength concrete. What's the highest concrete strength mix anyone here has seen or specified? In terms of newtons per millimetre squared. What's the highest strength that you guys can remember? 50? That's not that strong. That's almost lean mix. All right, Peter, in Ireland, I've been involved in a project. They're building I think it's in Limerick. They're building a bridge. I think it might actually be finished now. And the architect wanted a bridge with a very, very slender deck. And to get this very, very thin deck, the structural engineers specified incredibly high strength concrete. 100 Newton concrete. 100 Newton concrete. It's like iron. How do you make concrete that strong? What's the main thing you do to make it that strong? You increase very, very significantly the cement content. There are additives you add to it, but the main thing is you shovel a lot more cement into it as you increase the cement content. It increases. Be careful, gentlemen, when you're using very, very high strength concrete. I'm not saying you can cook an egg on it, but you'd come pretty close. But most of the time, if you're working in the UK and Ireland, 5 will be winter, 10 will be spring and autumn, 15 will be summer. Okay? Most of the time. All right. Turn over a couple of pages, gents. You'll see something that says Concrete Pressures Tutorial, I think it's 6. It will be RKF 206, and I think there's 8 questions to have a go at. Just give me a thumbs up that you've found the section. Okay. Use the new charts. Have a go at those questions. You need the charts for questions 1 to 4. You don't need the charts for questions 5, 6, 7, 8. So use the charts. And what I'd like you to do, gents, can you type your answers into the chat facility, please, so I can just make sure that you're all getting the right answers. So have you all got a chat thing on your in the menu somewhere? You can type your answers as you go along. Okay? So we've got about 20 minutes before we stop for lunch, so you can have a go at those 8 questions.
Wait, you said the question down.
It's section 206, AO. So find section 200, the one you've just been looking at.
Okay.
Think about another 2 or 3 pages. Has anyone not found it?
Ray, I didn't find it. I got only RKF 216, not 200 though.
206 are the questions.
Oh, okay, it's on the 206, is it? Okay.
Yeah, it says something like Concrete Pressures Tutorial 6A or 6 or something like that. Is that the page you've got? Let me show you what you're looking for. Let me see if I can find the... bear with me a second. What you're looking for is... share my screen view again.
Yeah, I got up to 210J, so...
No, it's before that. It'll be before that. If you can't find it, can you see it on the screen?
Yes, I can see this. Yeah, I can use that one.
Yeah. Maybe they've got your folder mixed up or something. You've got it wrong bit.
Yeah, I don't have that 200. The after 160, I got 210J.
Oh, okay, right. Do it off the screen then if you can't see it. Use the new tables. You've got it tells you what concrete group to use in the actual tables itself. You can see question 1 is a group A concrete.
You put answers in at the end, right?
We'll go through the answers. I'll tell you the answers as we go. But if you can use the chat bit and just just type your answers into the chat, please, and then I can monitor what's happening. Peter, have a look at question 3 again. You might have read it off the wrong chart, or you've done something wrong with question 3. In fact, Peter, is that 55 for the second one? Have a look at that one again as well. You might be on the wrong chart. Phil, have a look at question 1 again. What's your rate of rise, Phil? Question 1. Where's Mr. Thorpe? I've lost him. Where is it? Over here. Daryl, just have a look at question 2 again, please. The answer's not 50 for question 2. Where's Daryl gone? I've lost Daryl. Where is he? Mike Brown, yeah, question 1 is not 50. I think the mistake some of you are making is in the first question, the volume is 30 cube. You're putting it in at 15 cube an hour, so it takes you 2 hours to fill that shutter with concrete. Okay? But this is the mistake people are making.
The rate of rise.
Your shutter is 3 meters high. Yeah, the shutter is 3 meters high. You're filling it in 2 hours. Your rate of rise is not 2. That's the mistake people are making. You fill it in 2 hours, so your rate of rise is 1.5 meters per hour. Okay? Can you all see that? Yeah. The mistake some of you are making is you're putting a rate of rise of 2 on it. It's not a rate of rise of 2. Okay? It takes 2 hours to fill. So after 1 hour, your concrete's in the middle of the shutter. The second hour, you filled it. So your rate of rise is 1 per hour. Are you all getting the first 3 correct? 45, second one's 75, third one's 125. Question 4, you have to do the question the other way round. You've got to end up with a rate of rise. So you're doing the question backwards. For those of you who have got to question 5 and beyond, there's 2 parts of number 5. First one is, given the parameters in the question, what's the maximum possible pressure? That's what I'm asking you for. And the second part is, for that maximum pressure, how quickly can you actually pour the concrete? What's your rate of rise? With question 6, those of you who are not familiar with it, the double-sided shutter, we basically have 2 faces of shuttering and we fill the middle with concrete. Single-sided shutters, you've got 1 face of shuttering and the other side could be, for example, sheet piles or an existing structure. We've only got a single face of shuttering. you're all getting to grips with this, can I stop you and we'll run through the answer because I want to stop for lunch because we started a few minutes late. So I just want to run through the answers if I may with you. Let's get this sharing. To be honest, did anyone have a real nightmare with that? I don't think anyone really did. I think you're all reasonably happy with that. Right. So it's just this. So the first 4 questions, answer to the first was 45, answer to the second was 75. Exactly the same shutter. But can you see, question 1, the shutter was okay. Question 2, the shutter was not okay. Look at the difference in the pressures. It's a big... one thing to realise, gentlemen, is concrete pressures can vary massively. There are huge differences in them. Question column, and that is a massive pressure. That will be a bespoke design because you can't hire shuttering for that sort of pressure. That will have to be a bespoke design. Okay? And what I would expect people to do on site is question 4. Okay, so let's have a quick look at question 4 together. Can somebody remind me what concrete group I put in question 4? Was it? I think it was a group B, wasn't it?
Yeah,
Turn to chart B. I think I told you the temperature was 15, so they're pouring concrete in the summer. We were told that the shutter is 6 meters high because that's the concrete pour. And the hire company have told us that their shuttering can take a maximum pressure of 75. So what you do is you read along that 6 meters line, so you've got 15, 6 meters, till you get to 75 and then go up. The maximum you can fill it is 3 meters per hour. Gentlemen, the single most important thing about shuttering is rate of rise. This is how simple it is. If people fill shutters too fast, the pressure builds up, the shutter's probably going to burst. So go back to question 1 and 2. If we're using the same shuttering system for a long time on site, there's a good chance we could go from one season into another season. When can we pour concrete faster? Summer or winter?
Summer.
Summer. When can we pour concrete faster? Midday or midnight? Midday. The thing to look out for with shuttering, gentlemen, is rate of rise. If you're designing shutters, or more importantly, if you're checking shutters, you need to specify to your customer, this shutter works, providing you've got these parameters, and this is the maximum rate of rise that you should be pouring. This is how easy it is. If you pour a shutter too fast, the pressure builds up, there's a good chance the shutter bursts. And if you've never seen a burst shutter, this is what they look like. This is when I worked for Langs. I took this photograph a long time ago. I was in the office and my boss got a phone call, and this job happened to be quite close to the office. He said, we've had a shutter burst on us. So my boss said, look, come on, get in the car, we're going to have a look at it. So we drove to site. Now, my boss, he smoked like a train. Okay? He basically had a cigarette stuck to his lip all day. I reckon he slept with a cigarette in his mouth. Okay? And he got out of the car. The first thing he did was lit up a cigarette, went over to this, got his cigarette packet out, did a few calculations on the back of his cigarette packet, and he said to the site supervisor, he said, do you know what? I reckon if you'd have spent maybe 45 minutes longer pouring this, I don't think the shutter would have burst. And look how much money we had to throw at this problem. And by the way, this is before health and safety was invented. So that fella isn't on the ladder. They just pretend he's not there. Okay? The excavator isn't parked right on the edge. And that man isn't standing underneath the excavator, which is parked right on the edge. Can you see what we've had to do is demolish it and rebuild it? Simply because we poured it a little bit too quick. Rate of rise. Okay? Now, number 5. Given the parameters in the question, what's the maximum pressure? What's the maximum pressure at the question? What's the answer for question 5? Well, anyone want to guess at an answer? All right, how do we work it?
5.
Correct, 75. Why?
It's across the board. Yeah.
Pressure is just a weight times a height, isn't it? If your concrete weighs 25 and the height is 3 meters, the pressure cannot exceed 75, given those parameters. Okay, that's pressure. So the second part of the question was, if we design a shutter for that pressure, what does it mean for rate of rise? How quickly can you now fill the shutter? What's the permitted rate of rise?
Speed an hour.
Nope. Anyone else want to have a guess? Forget the chart. You don't need the tables. Forget the tables. You don't need them. What's the maximum speed we can fill it? All right. Well, let me give you a clue. What's it? If I've got this height times weight, what does my pressure diagram look like? It's a triangle, isn't it?
Yeah.
Yeah. Do you remember the theory we did at the beginning? I said the pressure diagram reduces. It does something like that. Why do we get that reduction? What's happening there?
Concrete is hardening.
Yeah. What we said was if we leave concrete alone for a period of time, it goes hard.
Yeah.
But what does it mean for the concrete if your pressure diagram is a triangle?
Not certain.
Absolutely. Your concrete is always fluid. What does that now mean for rate of rise if your concrete is wet? Rate of rise does not matter anymore. It is now irrelevant
Constant.
to rise. Yeah? What it means is you could pour the concrete as quick as you damn like. Like most contractors do on a normal building site. They throw it in as quick as they can get it out of the lorry. So the obvious question is, people say, well, why don't we always design shutters for that maximum pressure, for height times density, for height times weight? What do you think the answer is? Why don't we always design shutters for that?
It costs you more. You need more ties.
Absolutely. The problem is there, you end up with such enormous great shutters,
Yeah.
not economic. It takes, you have to hire a load of equipment. It takes an awful long time to physically put it all together. They're really, really heavy. You end up with massive cranes to move them. It's not an economic thing to do. And most of the time, we simply cannot get the concrete delivered fast enough. You can imagine a lorry of concrete trying to get to a site in the middle of London through the traffic. Yeah, it takes. We simply can't get the concrete there fast enough. So it's not economic to do that. Now, a couple of words of warning. Number one, the weight of concrete isn't always 25. You can get lightweight concrete, aerated concrete, light-hag, foam concrete, those sort of things. They tend not to be structural. You might be using them as backfill, perhaps. Does anyone a rough idea? What's the weight of something like aerated concrete, light-hag? What does that mean?
23.
It'll be a lot less than that. It'll be about half normal concrete.
10, 15.
Yeah, it'll be about 12, 13, 14, that sort of thing. Okay? So if your concrete has a density of 12 and your shutter's 4 meters high, it can't be more than 4 times 12, can it? The other side of the coin is you can get super heavy density concrete. There's a little bit of experience of, it's called biwritings. They use a very heavy aggregate, very dense aggregate, and to make it even heavier, they put lead shot into it. They fill it with lead concrete. It's unbelievably expensive. There is only one possible reason you'd want to use it.
Nuclear
One
power.
is to do with shielding from nuclear radiation. And so it might be for things like nuclear power stations, atomic weapons research. The other place you might occasionally find it, hospitals. Which,
X-ray room.
yeah, the X-ray department and that. What's that big circular scanner thing they've got? The what do they call them? What are they now? Is it MRIs?
MRI scans.
Yeah. So be careful with that stuff. It weighs about 3.5 ton a cube. And one other very, very unusual circumstance. Normally, we want to pour the concrete from the top of the shutter. Okay? And we have a chute to get it to, sort of guide it down to the bottom of the shutter. There are occasions where you can't pour the concrete from the top of the shutter. One example is you've got a bridge and you want to build a wall underneath it. Okay? And you can't pour the concrete in from above. Does anyone know how you could fill that shutter if you can't pour the concrete in from the top? What would you do?
You make shoots at the sides.
Almost. What you do is you bolt the pump to the side of your shutter, and then you force the concrete in under pressure, and you're using the pressure of the concrete to lift the concrete up the shutter. So you're not relying on gravity, you're going against gravity. Let me show you somebody trying to do this, a contractor trying to do this. It's near Coventry a few years ago. Okay? That's where they're going to bolt the pump, and then they're going to force the concrete in under pressure. And during a pour, it didn't go very well. Does that look like the plywood may have failed? Yeah? Look at the state of that shutter.
Jesus. Oh, pressure.
Those of you who have seen these members here, we call them soldiers.
Those don't bend easily. Those don't bend easily.
I'll tell you what, Derek, if you had to pick one of those up, you'd hurt your back, wouldn't you?
Yes, you would. Yes, you would.
If you dropped it on your foot, you'd know about it.
Oh, yeah, definitely.
They are big lumps of metal. You imagine the pressures and the forces required to distort to that manner. If you ever need to do something like this is a very, very high-risk, skilled operation. Okay? I would not recommend that you tackle this as your first ever design for a piece of shuttering. Okay? Once you've been designing shuttering for 5 or 10 years, have a go at this. This should not be your first design. Okay? When somebody just qualifies as a doctor, the first thing they do is not brain surgery. Okay? You might get them to do something like an ingrowing toenail or something like that. You don't get them to do brain surgery as your first operation. Okay. Now, number 6. We have a column, two-sided and one-sided. And I've asked you for highest and lowest pressures. Who thinks the column will have the highest pressure? Just give me a thumbs up. One. Is there only one person? Okay. The two-sided shutter will have the highest pressure. Nobody. So that means 11 of you think it's the single-sided shutter. Yeah? Okay, Phil, you're shaking your head. What? Is there another option? Now, unmute. I can't hear you.
They're all the same.
It's the same.
Who thinks they're all the same pressure?
Nah, I don't agree with Phil. I agree with Phil on that one.
There's
Correct answer. Column. Well done, Peter. Yeah. You can't buy that sort of experience, can you? Eh? Why is Peter correct and the rest of you are wrong? Why would I expect the column to have the highest pressure?
I think it has to do with the area.
Almost, Derek. Volume.
Yeah.
Did anyone bother to work out any volumes? If you work out the volume for the column, if you do a bit of pi squared times h, I think it's 1 point something cube of concrete. How long would it take them on site to pour just over a cube of concrete?
Not long.
So what we're saying is that column is going to be filled in about 5 minutes. What's your rate of rise? That's massive, isn't it? Four hours? What's your rate of rise now? Pick any one of the three charts. Doesn't matter, A, B or C. Does not matter. Look at any one of the three charts. Where are the bigger numbers? Walls and bases or columns? Where's the big number?
Columns. They're on columns.
Always
Columns,
expect
yes.
columns to have bigger pressures because you have so much less volume, so you fill them a hell of a lot quicker. Yeah, does that make sense to everyone? So one last one. Single-sided, double-sided. Okay. Is the pressure, and let's assume everything is the same, so same rate of rise, same concrete, same temperature, everything else. Is the pressure in a single-sided higher, lower, or the same as a double-sided? What do we think? Who thinks the single-sided gives a higher pressure? Who thinks the double-sided has a higher pressure? Who thinks they're all the same?
Depends on the dimensions, I guess.
Let's assume everything is identical, so same dimensions, same rate of rise, same day, same temperature, everything is the same.
Any pressure coming from the single sided increases the good pressure.
The pressure is always the same. Concrete pressure is concrete pressure. So I would expect those two pressures to be identical. I would not expect the shutters to be the same risk. Single-sided shutters are always a higher risk. Why? Okay. In a double-sided, all the pressure ends up in the ties and they work in tension. What's the purpose of this prop? What's the purpose of that prop?
It works in compression and keeps the shutter side pressure up.
It's to allow you to plumb the shutter up
Yep.
and to load over in the wind. It is nothing to do with taking the pressure of the concrete. All the pressure of the concrete ends up in your ties. In a single-sided, can you see this shutter is not tied to whatever this is? So these now have to take the load of the concrete. Let me demonstrate. My arm's going to be the shutter, the ruler's going to be the prop. If I represent this getting filled with concrete by pushing, what happens to the shutter? Is it?
You push and turn.
So somebody, I can't remember which one of you mentioned this earlier, uplift. The big risk with single-sided shutters, which is not really a problem with double-sided shutters, is uplift. You massive uplift with single-sided shutters. So what we've got to do is fix them down. This can be a really tricky detail to sort. You've got to anchor the shutters. Now, we'll come on to number 8 in a moment. Number 7. 2 minutes, because I'm very aware we want to stop for lunch. What happens if we pour concrete into that shape? This is based on a real job. When I worked for Kiers, we were pricing a job for the new airport in Addis Ababa in Ethiopia. And what they wanted was a little dam, a little concrete dam, and then they were going to allow water to build up here. And I think they were going to use the water for irrigation and probably for washing the planes. What happens if we want to pour concrete where the sides aren't parallel, where we've got tapering sides?
Rises quicker at the top.
All right, 2 things to worry about. Number 1, how does concrete pressure act on a surface? Perpendicular. The pressure will act perpendicular to a surface. Okay? Let's resolve the forces. So what we have is a horizontal component. So what we have to do is tie through the shutter. What other component have we got? We have a vertical component, so we have to anchor the shutter down. If you ever pour concrete onto a surface like that, an inclined surface, you've got a horizontal component to worry about and a vertical component to worry about. Okay? And the second problem, exactly what somebody had just said, we normally get the concrete delivered at a constant speed. So that the concrete company said, we can deliver a concrete lorry to you every 15 minutes. So, first lorry of concrete, you pour it into the bottom. Second lorry of concrete comes along. Third lorry of concrete comes along. What's happening to rate of rise as we go up the shutter?
Increases.
It's increasing. And what do we know happens to pressure when we increase rates of rise?
Pressure on the sides.
Pressure increases. This is actually quite a tricky little problem. What you need to do is to work out your rate of rise for each layer, okay, based on the height above the concrete. Then you have to plot a little graph of the pressure, and what you'll probably find is it looks a bit like that. Your maximum pressure isn't necessarily at the bottom of your shutter. It might be maybe somewhere around a third of the way up. Can you all see that? Because the rate of rise is increasing, there's a good chance the maximum pressure is not at the bottom.
Sure.
Watch out for this. And then the last one, we tend to use precast a lot. So here's an example of, it is a hotel being built in London, and it's just concrete Lego. And what they're going to do is fill this gap in here with concrete. So the precast concrete acts as a shutter. Okay? And your ties are these bars. It's the embedment of the bars into the concrete that acts as your ties. Okay, in the question, I think I've said this particular one we're using is 250mm wide, and it's an F3 system, which I think is this solid green line here. Okay? We've been told it's 3 meters high. That gap in there is about 100mm, and it's 10 meters long. So we need 3 cubes of concrete to fill it. Okay? These bars are at, I think it said 500 spacing. So let's look at the graph. So 500 spacing, we're on this 250 F3 system. So go up till you get to the solid green line. Read across. It tells you the maximum rate of rise is 1.5 meters per hour. How long should it take them to fill that? It's high, we're doing 1.5 meters an hour. How long should it take them to fill it?
2 meters.
2 hours.
Was, yeah.
I dare you, gents, tell your customer that you want them to pour 3 cubes of concrete in 2 hours. I dare you. Your customer say, what do you want me to put the concrete in with? A spoon?
Trucks will be backing up.
Absolutely. It is not practical to pour concrete that slowly. Okay? It'll probably go off in the back of the lorry. So what do we do? Okay. Number one, we can put props against the outside of the shutters, of the outside of the precast concrete, make it into a proper shutter. My argument then would be, why are you bothering with precast? Why not just build a shutter and do it in situ? Why are you wasting your time doing this? Number two, what about if we close up the spacing of these bars, make it stronger? So let's do the exercise. Instead of 500 spacing, what about if we did 350 spacing? We'll do the same exercise. So we go up to the green line, go across. Can you see? We've almost doubled the rate of rise. Yeah? Not quite, but we've almost doubled the rate of rise. But the wall system becomes more expensive because it's got more steel in it. For me, perhaps the easiest thing to do, instead of setting up 10 metres of this, what about if you set up 100 metres of it? Just set up a really long line, and then what you do is you fill it with concrete. So what you're doing is you're keeping the guys pouring concrete, keeping them busy, keeping the machinery and the men busy pouring concrete. Okay? If the men and the machinery are stood there not pouring concrete, you're losing money. Okay? Because the men will want paying. Whoever you've hired the machinery from, they will want paying as well. Yeah. So you want to keep the men and the machinery busy. So be careful with these sort of precast units. Okay, I think that's. Sorry, I've gone on a little bit longer. I think we'll stop lunch now. Has anyone got any questions on concrete pressures? Are you all happy that you understand the theory of concrete pressures? After lunch, we're going to apply it, and I'll teach you how to design some proper shuttering. Okay. So should we take half an hour? I've got 5 to 1, so should we kick off at 25 past 1? Okay. So
5 past 1.
yeah. So give me a thumbs up if you're all happy with that. Okay. So we'll see you enjoy your lunch. We'll see you in half an hour. Thank you. See you in a minute.